3D. So we'll just say, you know how what vectors are. Vectors are simply anything that has either magnitude and direction. It has to have both. And we'll specifically focus on the ones that are in 3D that are going to have a representation of I, J, and K. Remember, you have this guy, you know this already. And whenever we want to talk about the length of a vector, the formula we use to get the length of a vector is just modulus of that particular vector, which is, in this case, just going to be the A squared plus the B squared and plus the C squared. That's the length. In an event where they give you two particular vectors, let's say P, that has, let's say, A1, there's B1, there's C1, and there's Q, which has, let's say, A2, B2, and C2. And we want to find the vector PQ, because these are taken to be measured from the origin. So if we're looking for PQ, we want to have something that is going to be in the form of what? In the form of PO, then plus or Q, because we say the letters in between here have to be matching. We have to connect. It's like you have, this is OP. This is what you have, OP. Then we also have OQ. This is what we have. This is your OQ. Yeah, so if you want to get PQ, meaning we have to reverse this. We have to start from P going to O, then go from O, then go to Q. That's when we can just make the whole thing that can give us PQ from P to Q. We have to go from P to O, then O to Q. So we reverse the first one that we had, and we'll just sum up the whole thing. Your P, which was A1, B1, and C1, and your Q, which was your A2, B2, and C2. We can just add them up, considering that the first guy become negative now because we reversed them and we're adding them. So we'll take this as negative A1, negative B1, negative C1. We are adding it with Q, which is A2, B2, and C2. So meaning the vector PQ in component form is simply going to have A2 minus A1 with the I, then plus the B2 minus the B1. It's addition, but these are already carrying a negative. Now we're putting them on the right hand side. That's J. Then you have C2 minus C1. This here gives you OK. And if you want to get the distance between two vectors like the way we had here, meaning you just proceed and square these components. Yeah, that's where the whole formula comes from, actually, to say, if you want to talk about the distance from P to Q, you just say the distance PQ modulus is just going to be equal to A2 minus A1, where we have landed minus where we are coming from. Each component subtracting, then squaring them. Yeah, so I have, this is B2 minus B1, then you square this, then you have your C2 minus C1 as well, then square them. So this is the distance or the length, the distance between two particular vectors or 2 points. So this is already okay. Then there are certain properties we have to learn in terms of vectors, like the angle, the dot product. So those are the things I want to highlight here. So if you have two vectors, let's say U, vector U, which is A1, I, then you have B1, J, then you have C1 with a K, then you have V, which is A2I, and B2J, then plus C2K. If you want to find the dot product, the first thing is the dot product. Yeah, so the dot product, which is U, point and V, this is just the same as the length of V or U, the length of this, then cos the angle between them, the angle between these vectors. Yeah, and you should be reminded that whenever we're multiplying, the whole multiplication that we're going to do is that whenever you multiply I and I, this gives you 1. I and I is a 1. It's just like a cyclic thing. Then J, the same applies to J and J, the same letters, J and J. Then the same applies to K and K. Then the last thing is that if you're multiplying any different letters, everything becomes 0. That's the reason why if you're multiplying two vectors, we have to multiply the I component and the I component plus the J component and the J component, because anything with different letters like I times J, for instance, or k and j, or I and k, everything gives us a 0. Yeah, so please take note of this. And the angle that is formed is just going to be the angle between the tails that you have. So like the intersection where the two guys are going to be joined, that's what we consider to be the angle between the two vectors. Yeah, so mostly the angle is always just going to be between 0 and 180. That's the usual case. Yeah. So the easier way to get it, let me give us an example here. The proper example. So just these two properties before we talk about an example. That these two properties you have to know as well. If you have two vectors that are non-zero, like the way we had the u and the v, you have u and v. They are not zero vectors, meaning their length is not 0. They are something. They are above 1 and above. Yeah, so it simply means if you have, the first property says if you have v, we can have a scalar that can map u to v. So there's always that particular number. Could be a fraction or anything, an integer. There's always, alpha is just a constant. Yeah, so these two can always be related by a constant. There's like a proportionality constant. Then the second thing is that the angle between them should always the angle between this is specifically for parallel vectors. Let me just write here. If two of these are parallel, the angle between them should either be 0. The angle should either be 0 or 180. That's what we have. If two vectors are parallel. Then if two vectors are perpendicular to each other, so perpendicular vectors, so if they're perpendicular, the same u and v, they are two non-zero vectors, they're not zero vectors. The first property is that their dot product is always going to be 0. If they are perpendicular, that is 90 degrees from each other. So the angle between them, of course, should be 90, obviously. So these are the two properties that you need to know. And just another note, again, you can add on to what we have so far. So provided we're using the x and y direction, to find the value of a, sometimes we can use this other expression here. They're like proportions, depending on where the whole thing is placed. So we're saying if alpha is defined as an angle between the positive x-axis and your vector v, for instance, we can have the following angles that can be listed. So we could have cos alpha could have been the same as a over the length of v. Then cos beta. These are angles where the vectors can be found. Depends on the x, y, or z axis. These are called directional angles, sort of. Yeah, so these we call them directional angles. So we have the second term with its the j component. Then over that, then we have the other one, which is cos y, or cos gamma, this guy. This is c over this, provided your v is the one that is giving us the a, the b, and the c. Yeah. So let me give you an example here, and I want us to have a proper example just as soon as I'm done with these last properties here. So the last thing we're going to talk about is projections. If you're given two non-zero vectors, so projections, we can project one vector to another vector, and the formula is just that if you're projecting, let's say we're projecting v onto u, so v is the one that we write there, then the u is there. This is just supposed to be v times u, the dot product on top there, then over the length or the modulus of u squared, then multiply by the vector u. That's the formula. So if we were doing the other way around, if we were saying we're projecting u onto v, this would have been the dot product. We start with the guy we're projecting onto the other one. So this is uv, then down here would have said v squared, then multiplying the vector v. So it matters which one we're projecting onto the other one. Yeah, and if you want to get the component, there's what we call the component of vector v in the direction of u. So component of, let's say, of v in the direction of u, the formula is almost going to be the same as the projection, but it just has the length down and there's no vector this side. Yeah, so these are the only two formulas we need. This is the same as this. I was just saying, depends on the letter you're projecting onto the other one. Yeah, so if we're projecting our u onto v, this is what we have. Our v onto u, this is what we have. So let me give you now an example. We've done the properties. Let me give you an illustration. So example, you have vector u, which is equal to 2i, then plus j, then plus k. This translates to be what? It's the same as 2, 1, 1, right? This is like that. Then you have your v, which is already given as I plus j. So meaning this translates to be what? Your v is equal to, there's a 1, there's a 1, there's a 0. So it translates to that. And our alpha happens to be 2. So the alpha is just a constant, like the way we say it. So the first thing they want us to do is to get the angle. First we say the summation. Let's get u plus v. Let's see what we can get. And the second one, I want us to get the dot product. Let's just say, yeah, the dot product first. Let's say this. Let's say the angle between. So angle between u and v. Then the next one, number 3, we need to project v onto omega or w, provided that where our w is the same as alpha times v. That's how we produce vector w. Then the last thing they want us to do is to find the component of u onto n. N is a whole different vector as well. So where, again, they give us how to get n. N is equal to u minus alpha w, or v, I mean. This is a v this side. Yeah. So these are new vectors. W and n are new vectors that we're going to produce using our formulas. So the first thing here, they want us to get the summation of u and v. That's what they want. They want just the sum, just adding them. This we can do it directly here, because this is just going to be us adding the like terms, right? Like the x and the y and the z, just adding them. So this is just going to give us a 3. This is going to give us a 2. That's going to give us a 1. So this is the vector u plus v. That's what we get when we add them. We have vector uv with a constant alpha, and we want to get these two questions that have been given to us here. So the first one is easy. They just want us to get the summation of u and v, which we have by adding the matching components. So x and x, y and y, z and z. So this is can also be written as 3i, then plus your 2j, and plus your k. So this is, it's okay even if you leave it like this. Then the next part, they want us to get the angle between these two guys here. So the first thing we need to get is the dot product, the u times v, right? Before we get the individual moduluses. Yeah, because the angle between two vectors is supposed to be given as what? Those, let me write it here. So solution. Yeah, so the angle between two vectors is just going to be those two vectors multiplied over 1, the length of u and the modulus of v as well. Yeah, so their dot product, if I'm to rewrite them here, remember our u is what? 2, 1, and 1. Our v is what? Is 1, 1, 0. Yeah, so their product, if you multiply this, 2 times that, that's a 2, plus 2 times that, 1 times 1, I mean, this is a 0. This just gives us a 3. Right? Yeah, that's their dot product there. That's a 3. Then we need to get their individual moduluses or magnitude. So the magnitude of u is just going to be 2 squared plus 1 squared plus 1 squared. That's a 4, 5, 6. Is it? Yeah, so we have modulus of 6. The square root, of course. This is that. Then for v, we're having 1, 1. That's going to give us a 2 by the time we're done solving for this guy. Yeah, so meaning the angle we're interested in is that cos theta is equal, there's a 3, down there is a root what? It's a root 6 and a root 2, which in your case, since you guys use calculators, you can just easily punch this. So theta is cos inverse of 3 over, that's the same as root 12. Now, because I'm not having a calculator on my end, I'll try to use trig. This is going to be 3. This is the same as 2 root what? Root 3, is it? So if we have what? Because this is the same as root 4 times root 3. So this is a 2. That's the reason why we're having this. What do you get if you say cos inverse of this guy here? Making sure your calculator is in degrees. What do you get? I think this should be a 30. If you rationalize this, that's root 3. Yeah, this is going to be, I think it should be a 30 or pi over 6 in radians. So I don't know what you are getting. I'm just trying to rationalize this. Here, if you rationalize with root 3 and root 3, this is going to give me a 3 root 3 over a 2 and a 3. This can cancel. The only special angle that gives us root 3 over 2 is for cos is 30. So that's how I'm getting a 30. Yeah, and remember we said the angle has to be between 0 to 180. Of course, we know that 30 gives us another angle in the fourth quadrant, but that's a little bit bigger than the limit of where our angle between two vectors should lie. So we won't consider the 330. There's another angle, of course, here. There's 330. But we'll discard it. We'll just focus on this one, which belongs to the interval 0 to, so our theta should be between 0 to 180. Yeah. So our theta is 30. Then the next question is asking for the projection. Yeah, we're projecting, that's part C. We're projecting V onto W, where we know to say W is the same as alpha times V. So alpha is 2, our V was 1. So that's a 1, there was a 1, 1, 0. So meaning W is the same as what? 2, 2, 0. Hope this is okay. Yeah, so now that we know the vector here, the vector W, we know the projection of something. Let's say this is V onto W. That's going to be the same as W times V, the dot product, over the W squared times the W vector there. Yeah, so the dot product, if V is what? V is 1, 1, 0. The dot product, W and V, is just a 2 plus a 2 plus 0. That's just a 4. Right? The modulus of this guy squared, meaning that's just 2 plus 2 plus 0. That gives us 4, 4, that's 8. Yeah, so this is the same as there's a 4, there's 8, multiplying the vector W. So this is so it simply means like a shadow, so to say. It's like the shadow of V that, yeah, so this is the answer we're getting. Then the next one is they're saying they want the component of U, as we have components of U towards N. So they're saying the last one was the component of U towards N. So the formula for the component is supposed to be the dot product of the two guys given, that's U and N, then over the modulus of the guy we are going on to, so that's N. And remember N, we said N was given as what? N was given as U minus alpha, then we have V this side, that's what we said. So to get our vector N, the U was 2, is it 2, 1, 1? then minus our alpha was this. Our V was 1, 1, 0. Yeah, so we have 2, 1, 1. And this is 2, 2, 0. This will give us a 0, negative 1. That's a 1. So this is the vector n. Yeah, so if we have your n, then we do the same thing again. We get the dot product. The v is 1, 1, 0. This is a 0 plus this is negative 1 plus this is going to give us what? We're saying 0 times this times that. That's negative 1. And the last one, just a minute, this is what? 2 times, because it's what? It's, we got this part which is a 1, is it? Oh, sorry, here. This is, yeah, this is a 1, right? This is a 1, because we said 1 minus 0, yeah? This is our n. Yeah, so we have our n there. Then our v is what? Our v is supposed to be, this is what? Oh, this is u, sorry. This is our u. Because we are finding the component of u towards n, so we need our u, not v. Yeah, so u is the same as 2, 1, 1. So the dot product here is supposed to be, that's a 0, negative 1, plus a 1, that gives us a 0. Meaning the answer here is just 0. We don't care what n modulus is going to be. Everything is just going to be 0. Yeah, so whenever we get the component to be 0, it means that the vector u is actually orthogonal to vector n. You know what orthogonal means, right? Okay, so what we mean by orthogonal, the same way that we have parallel and so we have these 3 terms that we'll be using. Yeah, we have parallel, then we have perpendicular. Yeah, so parallel, perpendicular, then if we say they are orthogonal, we just mean that their dot product is 0. Yeah, that's like the general property. So geometrically, we just mean the angle between them is they are like 180 degrees apart from each other. So it's like one is facing in the other direction, the other one is facing in the other direction. So yeah, so the dot product, yeah, so dot product is equal to 0. This guy here. Yeah. Is this okay? That's a little bit interesting. Apart from these simple properties of vectors, we want to talk about lines in space. Yeah, because these vectors are going to create lines. Yes, let me just mute you. I'm getting feedback in the background. Okay, yeah. So we want to talk about lines in space. And there's always a question during exams about this. So lines in space, it doesn't miss. Yeah, lines in space. So imagine we have 2 points. Let's say we have a point here, which is x naught and y naught. Then we have z naught. Then we also have q, which is, let's say, x1. Let's say y1. Then we have z1. These are 2 particular points on a line. These guys are on line L. So let's say they're on a line L. In an instance where we have a vector connecting these 2 points, let's say we have vector v. There's a vector v which is simply running from P to Q, connecting these 2 lines. Of course, meaning we're going to get what? The same thing that we did. This is like OP, this is like OQ. So the vector is going to have the following components. It's just going to be x1 minus x naught. Then the y part is going to be y1 minus, the j part is going to be this. Then we're going to have the z part, which is z1 minus z naught. So these will be like the components of that particular vector that is going to be running parallel to the same line in space. Yeah, so we have 2 points that are on a line. This is our line L. We have point what? Point, let's say point P, we have point Q. We're saying there's a parallel, there's a line, there's a vector rather, which is called V, PQ, parallel to those 2 points, the line joining those 2 points. And if there is another line, another point, let's say if if r, x, y, and z is another point on the line L, then PR, wherever R is, whether R is located, let's say we put it here, even if we put R there, let me use a different color. It doesn't matter where it's located. Could be within the PQ or after it. We really don't mind. We're saying as long as there's another point R, PR is also going to be parallel to what? To PQ, the line, the vector PQ, the line or the vector PQ is this guy here. So even another line that is still, that is going to be created by a point on the same line again, it will give us the same outcome. It's still going to be parallel to this, to PQ, meaning they can actually be related by some element T. We can just say they are going to be related by some element T. We are going to make up an equation that says the OR, so let's say from the origin, so we have an equation that looks like this. Yeah, so we have the following outcome saying PR is actually just the same thing as T times V, because either V will be larger than PR or it will be smaller than PR. It doesn't matter. All we're saying is that there's a constant T connecting them. It's like your alpha. Now we're just using T. Yeah, that's basically what we are having. Yeah, in 3D. Yes, the direction vector, exactly. Yeah, because in 3D it's actually going to look like let's say you have your Z, you have something like this. This is let's say you have your X, then you have your Y, and you have your Z here. And we want to show these 2 points. So I'll show to say, imagine there's OP, there's some point here. P is somewhere there. Let's say P is here, located there. Let's say there's R is here. Q happens to be here. Yeah, so we'll just say there's some line that we can connect here that connect these two guys. So here they made it in such a way that R is not between P and Q, but it's actually after Q, but it's just the same thing. They're all going to be joined by the same line because they're all on the same plane, sort of. So it creates an equation that says we have OR. If you're looking for OR, this is just the same as OP, then plus PR, this guy here and this guy, which is just the same as OP. Because from here, we're going to have what? This is the same as OP, which can now be added to T. Because we said OR, or rather we say what? PR. PR is the same as this, you know, it's PR. It can give us T times V. So let me just, it's okay even if this doesn't make sense. I just want you to see that we're going to create the original guy, the O to R, which is X, Y, and Z. Are going to create equations. Now we're saying we have the first thing, which is the first point we're at, the X naught, the Y naught, and the Z naught. Then we're having T multiplying the V. The V is the PR. Remember, PR is just the difference between the PQ that we had, the difference between the 2 points. So which is just going to be X1 minus X naught. That's the first component. So we have something like this. Again, you have the other guy. Let me just write it back here. So this equation, the good part, even if you are not able to follow through, you can just like know this. I'll show you when we do an example. You'll see how this is just going to be the same all the time. The first point, X naught, Y naught, and Z naught. Then there is a plus T. Then this is X1 and X naught. Then we have Y1 and Y naught. Then we have Z1 and Z naught. Yeah, so this is going to create an equation because we're now going to equate what? We're going to equate X. This is X, right? X to X naught multiplying T times this guy here. If we let this part here be A, if we let this part here be B for some random vector, this is, let's say, C, then we're going to say this X that we're having is equal to this X naught plus AT. Then the other y value is going to be y naught, then plus ab. Then again the last one, which is the z is equal to the z naught plus a. This is not t, sorry, this is ta, yeah, this is supposed to be at, because t is multiplying the a, then this is going to be bt, and that's going to be ct. So these three equations are going to be the parametric equations of the line L that we had. We can also change them and write them like this by making, we make a and b to be the subject of the formula. That's just going to give us, a is going to give us what? X. The first part, we're making, is it t? We're making t the subject, yes, in each case. That's x minus x naught over t. Over what? Over a, I mean. We're making t the subject. In the next one, so we're saying it has to be the same as, if we say y minus y naught over b, it has to be the same as z minus z naught over c. So t is the same thing, because even here there's a t, even here there's a t. So no wonder we're equating all of them, because it's one letter, it's t. It has to be equal to each of these guys. For any vector, which is a, for any vector, this is a directional vector. So note that the vector v, the one that we got the a, the b, and the c, is the directional vector. Yeah, so let me give you an example of how this can help us. Let me just give an illustration. So the example here, they're saying find the equation, the equation, the vector equation. So they're saying find the vector equation, the parametric equation. Oh yes, yeah, the question starts from here. So the question says find the vector, parametric equation, and symmetric equation, and the symmetric equations of the line L described as follows. The question is just here, the first one, part 1. The line that passes, L passes through the point 2, -1, -2, and then it's parallel to the another vector, which is negative I, this guy here given. So this is the parallel, the vector we are parallel with. This is the initial point that we are only given. Yes. So first of all, let me give you the general idea, in case you didn't get anything that I said previously. The general idea is that if you're looking for the, if I may give us the general idea, for the sake of those who are just going to watch the video, let me just, so the general idea here, first of all, the expression, everything that you need, just a summary on the vector equation and everything else. So whenever you have a point, let's say x naught and y naught and z naught, and we have a parallel directional vector, let's say v, we call it a, b, and c, and you're looking for the vector equation. So the first thing is vector equation. Vector equation is always r is equal to r naught. So this is like the x values that you are given at the x, then this is like these x naughts that you have the point, then you have t times v, which is the directional vector given there. Then the second thing, if you're looking for the parametric equation, we just make what? We just make, we have x is equal to x naught plus at from this, then you have y is y naught plus at. This is the easiest when you just have one point. Then z is equal to z naught plus what? Plus, is it ct? This is supposed to be bt. This is ct. Yeah, then the symmetric equation is when you just decide to make t the subject in each case. Yeah, so symmetric, we'll just try to say from here, just say x minus x naught over your what? Over your a should be equal to y minus y naught over your b should be equal to z and z naught over your c. Yeah, so with the information given in our question, according to the data that we have to solve number 1, the point that we are given, the p, is 2, -1, -2. And the vector given, our v in our case, giving us our ABC is -1, 1, and -1. So the vector equation should be, so we'll just say our vector, let's call it v. Should we call it v? No, v is already used there, so let me call it u or anything. Let me call it r. It's going to be this guy, this guy here, then we say plus t times this guy is here, -1. So r is equal to, there's a 2 minus t, this guy there. Then there's this part which is what, -1, then plus t, and there's the last part which is -2 minus t. So we have this. Yeah, then the parametric equation, we can just say the x1, the x component is 2 minus t, the y1 will be -1 plus t, then the z1 is -2 minus t. The symmetric one is we make t the subject here, that's going to give us x minus 2 over -1, should be equal to y plus 1 over 1. Then this is z plus 2 over 1 as well. Is it -1 there, right? Yeah. So these are the symmetric equations that were needed. This one was simple, right? The first one was okay, isn't it? Yeah, now the next one they want us to get between these 2 points. So we have 2 particular points. Yeah, so part 2, it's a line that passes through these 2 points, which is what we have. Well, it's like you have your P, which is 1, 0, and -3. If you just like go back, you see this. And this one you have a 2, 1, and 0. So the first thing we need to know is to find the direction of vector. Yeah, the direction of vector is supposed to be, in this case, is like we just say summation of this, like we're looking for a PQ. So the direction of vector is going to be, others will just say same as Q minus P, for instance. So it's just the same as 1, the same as 1, it's the same as negative what? It's 3, it's a 3, it's positive because we're subtracting it. It's 0 minus -3, so yeah. Yeah, okay on this part? Yeah, so the vector equation now is going to be, I'll just use r as well. The first point, these are the initials, we write them there. We're going to have 1, 0, and -3, then plus a t, and the, yes, the x notes, the notes, yeah, they're the ones that we always use. Yes. We always use the x note. Oh, they'll list it first. So like here, this is the, yeah, they'll list it first because we're passing from this guy to that guy. So yeah, it's even here, it's like your PQ. So yeah. Yeah, this is going to be a t, then this is going to be, that's a 0, that's just going to give us a t there. Then we have z, which is equal to -3 plus 3t. Yeah, then we can make x minus 1 over 1, the symmetric guys, y minus 0 over what? Over 1. Then this is just z plus 3 over 3. Yeah, so we have the symmetric equations, right? Yeah. This is okay.